of a new system of differential equations that we call the Hitchin constant scalar curvature system. So all that I'm going to talk about is joint work with my supervisor, of course, Jacopo Stoppa, also in SISSA. Okay, so the general setting is that of the CSCK problem. So we have a compact Kähler manifold over which we fixed some background Kähler form omega 0, and we look for new Kähler forms in the same class that have a constant scalar curvature. So I'm writing the equation like this. So S is just the scalar curvature of the corresponding Kähler metric, and this will be a constant that in general depends just on the topology of the manifold plus the Kähler class that we have fixed. And the problem, as stated, is quite difficult because, well, it's a fourth order fully nonlinear partial differential equation if we parameterize the Kähler class via the del-del bar lemma. So we write any Kähler form as omega 0 plus the complex hessian of some function. Then this equation becomes a fourth order equation on F, and it's highly nonlinear, so quite difficult to study in general. At the point of view we want to take is that of this remark by Fujiki and Donaldson, and they showed independently that this equation can actually be considered as a moment map equation for some infinite dimensional action. So we have an infinite dimensional Kähler manifold, this curly J here, and we have an action of some Lie group, also infinite dimensional, and this action is Hamiltonian, and we can realize the scalar curvature equation as a moment map equation like this. So this is interesting for us because it tells us that there should be some kind of algebraic notion of stability that tells us when we can expect to have solutions of this equation. And this is motivated by, let's say, this Kempfness theorem of GIT, but of course the Kempfness theorem is a finite dimensional phenomenon, while in our case we are in an infinite dimensional setting. So there is this stability picture for the CSCK problem is still very much conjectural, at least for most cases. And well, then there has been a large body of work on this on trying to characterize this stability condition, if there is any. Okay, so let me get a bit more into the details of this moment map picture. So our infinite dimensional manifold will be this curly J that is the set of all almost complex structures that are compatible with some fixed background Kähler form on our manifold X. And here, well, you can actually consider just integrable complex structures. It doesn't really change much, and for our purposes is actually more important. So this is a Kähler manifold of infinite dimension, and if we fix a complex structure in J, then the tangent space at this complex structure consists of all first order deformations of the structure. So we have some endomorphism of the tangent bundle that exchanges the holomorphic and the anti-holomorphic part. That also satisfies some additional compatibility condition with the background form. And the Kähler product is can be written like this. So anytime we have two such objects, we can consider the composition of alpha with the conjugate of the second one, and then so this is an endomorphism of the holomorphic part, and we can just take its trace, and the real part of that is a Kähler metric. So the group that acts on J is the group of all symplectomorphisms that have a Hamiltonian potential. And this action is Hamiltonian. So this is the theorem by Fujiki and Donaldson that the moment map for this action is given by the scalar curvature of the metric. Okay, so our goal here is to take this whole picture and to upgrade it to a hyperkähler reduction. So we consider the holomorphic tangent bundle of J. So this T star will always be the holomorphic part of the cotangent bundle. And we want to define a hyperkähler metric on this space and see if the action of G is still Hamiltonian. So more precisely, we will find some hyperkähler structure on this T star J, such that the zero section is a Kähler embedding. So the metric of the cotangent space is restricts to the usual Fujiki-Donaldson metric on curly J. And the action should be Hamiltonian with respect to any Kähler form in the hyperkähler family. Okay, more precisely, well, we will just find three Kähler forms that generate a hyperkähler family of symplectic forms on the cotangent space of J. And omega-1 will be an extension of the Donaldson-Fujiki symplectic structure. And also the action of G will be Hamiltonian with respect to these three forms. So the problem has already been studied, but just in the case when X is a Riemann surface. So for complex dimension 1, this has already been done by Donaldson in 2003, and also has been studied by Tom Hodge in his PhD thesis a couple of years later, but we'll get back to the results in a few minutes. Okay. Instead, what I'm going to propose now is a construction that works in any dimension, and hopefully it gives us some interesting set of equations. Okay, so the motivation is essentially the same as in Donaldson's work. So it comes from the theory of the Hermitian-Yang-Mills equation. So much of the study of the CSCK problem, particularly from this algebraic stability side, has been inspired by the already well-developed theory of the Hermitian-Yang-Mills equation. So let me recall briefly what this equation is. And we fix a Riemann surface X with a fixed Kähler form on X and a holomorphic vector bundle on the curve. And now the equation is stated for a Hermitian metric on E, and it's an equation, it's a condition on the curvature of the metric. So we ask it to be proportional to the fixed Kähler form. Now this lambda here is just a constant, and is essentially what is usually called the slope of the bundle E. Okay, so this is also a moment map equation for some infinite dimensional action, and this is a result by a TEI and bot. And the action here is that of unitary gauge transformations that act on the space of all possible holomorphic structures on the bundle E. Okay, so yeah, lastly, we know that the existence of solutions to this equation is equivalent to the bundle E satisfying an algebraic condition that is usually called slope stability. Okay, so then this is all the classical picture for this HYM equation. And now Hitchin, some years after the work by Atiyah and bot, studied a slightly different system of equations that can be considered to be an hyperkähler extension of the HYM equation. So he defined a hyperkähler structure on this space, on the cotangent space of A. Now, recall A is the space of all possible holomorphic structures on the bundle E. So this is a fine manifold, infinite dimensional. So its cotangent bundle is just a product space of A with this one forms. And so this hyperkähler structure extends the Kähler structure of a Tia and bot. And he showed also that the induced action on this space is Hamiltonian with respect to every Kähler form in the hyperkähler family. So this is a way to formulate Hitchin's Higgs bundle equations. So we take in particular two of the symplectic forms in the hyperkähler family. So the first one, this theta, is just a complex combination of omega 2, omega 3. Then we have omega 1. And we find a system of equations for two variables now. We have a Hermitian metric and a Higgs field, so a 1-0 form with values in the endomorphism. And the moment map equation with respect to this symplectic form is just a holomorphistic condition on the Higgs field. While for the first symplectic form instead, you see we find an equation that is that looks like a modification of the Hermitian-Yang-Mills equation. So if phi equal to 0, then this term here vanishes, and we just get the usual Hermitian-Yang-Mills equation. But in general, we add this commutator term. Okay. So here I'm summarizing some aspects of the theory of the HYM equation and the CSCK equation. So they are both moment map equations for some infinite dimensional action. And here on the left-hand side, we have a couple of results for the HYM equation that sort of inspired directly, more or less, some results on the CSCK theory. So for example, the bounds on the Yang-Mills functional have inspired Donaldson to find lower bounds for the Calabi functional. And this is a really important result in the study of the constant scalar curvature equation. Then we know the HYM equation is sort of equivalent to slope stability. And this prompted many people to formulate this conjecture that the existence of solutions to the CSCK equation should be equivalent to some form of K stability. We don't know which one yet, but well, we're getting to it. And so our work of Jakob and I is to sort of extend this symmetry, this relation between the two problems to this hyperkähler upgrade. So here we have the whole theory of Higgs bundle that have a really rich geometric structure, and we are trying to fill in these question marks here. Now, what I'm going to talk about is just how to fill in this particular one, that is how to define in a sensible way a Higgs term for the CSCK equation. And because these other 2 points are still wildly open. So maybe I'll have some updates in a few years, but for now, we'll just have to see how one can define a hyperkähler upgrade of the CSCK equation. Okay. So our base object that we want to work with is this set J of all complex structures that are compatible with some fixed Kähler form. Now we have a slightly different characterization of this manifold as the space of all the sections of some fiber bundle. So we have a fiber bundle F over our base X, whose fibers are all isomorphic to this Hermitian symmetric space. So we have the symplectic group here, quotiented by the unitary group. This is usually called the Seagal's upper half space, is one of the many generalizations of the hyperbolic plane. Moreover, this fiber bundle trivializes anytime you fix a system of Darboux coordinates for your background Kähler form. And if you have two different system of Darboux coordinates, then the transition function is just a translation by the action of SP to N. So this description of curly J is particularly interesting for us because there's this important result by Bicard and Goduchon that in 97 constructed a hyperkähler structure on the cotangent space of any Hermitian symmetric space. And moreover, this hyperkähler structure that Bicard and Goduchon find is an extension of the metric on the Hermitian symmetric space and is invariant under the action of the group, so the action by translations. And moreover, this hyperkähler metric is also unique with these properties. So you see that then we can use this theorem by Bicard and Goduchon in our case. So we have some fiber bundle with whose fibers are a Hermitian symmetric space, and the change of the trivializations acts as translations by the group. So this means that we can take the Bicard-Goduchon metric on the cotangent space of a Seeger's upper half space and sort of glue them together over X to define a hyperkähler metric on the cotangent space of J. Okay, so let's also look at the lift of the Hamiltonian action. And so the Bicard-Goduchon metric is obtained by a Calabi ansatz. So this means that it's actually quite easy to prove that the lift of the action is Hamiltonian with respect to this hyperkähler structure. And so we find indeed a system of moment map equations, because it turns out that our action on curly J can be lifted to an action that is Hamiltonian with respect to all the symplectic forms in the hyperkähler family, as was also the case for Hitchin's equations. And so we find a new system of moment map equations that should be analogous to Hitchin's system. So the variables now will be a Kähler form, omega, and also a first order deformation of the complex structure. So this is a 1-0 form with values in the anti-holomorphic bundle of X. Good. Okay, so the system looks like this. So we call it the Hitchin-cscK system, or well, for brevity, HCSCK. The HCSCK system, it has one major difference from Hitchin's equations, in that the two variables are, enter in both the first and the second moment map equation. So here you see that we are computing the divergence. So this is a metric quantity depending on the Kähler form of the del star of alpha. Now, this is sort of a weak holomorphicity condition on alpha. Oops. And the second moment map equation that we usually call the real moment map equation is a modification of the constant scalar curvature. So here we have a constant scalar curvature term. And then we have to add the divergence of some vector field. So we modify the constant scalar curvature equation to a new, slightly more complicated equation. Now, this X of omega and alpha is a vector field that I'm not going to write down right now, because its expression is slightly cumbersome. And also because to write down its expression, I first have to make some remarks on the geometry of this infinite dimensional hyperkähler manifold, T star J. Okay, so the first remark is that the hyperkähler metric defined by Bicard and Goduchon is not defined on the whole space, but just on an open neighborhood of the zero section. Moreover, this metric is not complete on this neighborhood. So this is an issue for many reasons. And it forces us to consider a hyperkähler metric defined just on an open submanifold of the cotangent space of J. And so this open submanifold consists of every first order deformation whose eigenvalues are less than 1. So, well, more precisely, we have to take an first order deformation alpha. Then alpha and alpha bar, this composition is similar to a Hermitian operator, positive definite. And we ask its eigenvalues to be less than 1. So remember, this is a positive definite operator. So this means that, first of all, in the Hitchin-cscK system, we actually have to impose some additional conditions. And so the first one is that the eigenvalues of alpha, alpha bar should be strictly less than 1. So this R is just a condition on the spectral radius. And a second condition is compatibility between omega and the deformation of the complex structure. Okay, so with everything in mind, now we can give an expression for that vector field that appeared in the previous slide. So alpha alpha bar is similar to a Hermitian matrix, positive definite. And since its eigenvalues are less than 1, this identity minus alpha alpha bar is still positive definite. And we can take its square root. Then take its inverse, and this gives us a new endomorphism alpha hat. And our vector field is written in terms of the first order deformation alpha and this new endomorphism alpha hat. So it's the real part of this huge combination of terms. And so here we first have something that looks like a commutator part. And then some additional vector field that instead doesn't have a direct parallel in Hitchin's system. So our system of equations is much more complicated than the Higgs bundle equations. Okay, now since to study the system we have to compute this matrix square root, the equations in general are quite difficult to study. And well, in dimension 1 and 2, this can be done quite easily. And in fact, in dimension 1, this has been done by Donaldson, as I already mentioned, in 2003. Well, for dimension 2, we have some first results that I'm going to talk about in a few minutes. So let's see what happens in dimension 1. So well, a special set of solutions has been studied by Thomas Hodge in his thesis. And we have an existence theorem. So what can we say? Then in complex dimension 1, the first moment map equation is quite easy to solve, and the solutions are always parameterized by pairs of an abelian differential, this beta, and a quadratic differential tau. So the problem is unobstructed in the sense that for each fixed initial data, let's say beta and tau, then we can show that there is a unique Kähler form that solves the Hitchin-cscK system. So in dimension 1, the problem is unobstructed, as you would expect on a Riemann surface. Everything becomes much easier. Now, this special set of solutions mentioned here, studied by Hodge, essentially corresponds to setting beta equal to 0. So he studied a codimension G, where G is the genus of the curve, set of solutions. But his existence result is much sharper than ours. So we will have to pay a price for also taking into account this other term, beta. Okay, so instead what happens on surfaces is maybe a bit more interesting, because, well, on a complex surface, we find the first obstructions to the symplectie problem. So on a surface, we know that that sometimes there is no solution of the symplectie equation. So one might wonder, okay, there are no solution of the symplectie problem, but maybe if we choose a Higgs term in an appropriate way, maybe we can find solutions instead of our more general system. So we consider in particular this classical example of a ruled surface that has no constant scalar curvature metric, in fact, in any Kähler class. And this can be checked, for example, by computing the Futaki invariant of the surface. It's non-zero. But so our first result on the Hitchin-cscK system actually was that you can choose a deformation of the complex structure of this surface such that the Hitchin-cscK system has a solution. So we fix the hyperbolic metric on the base curve, and we make a Calabi ansatz. So we make a Calabi ansatz that depends on a parameter m. So this is a positive real number. This is more or less just the volume of the fibers of the ruling. So we show that if the fibers are small enough, then you can always choose a deformation of the complex structure and a Kähler metric that solve the Hitchin-cscK system. So this is sort of a perturbative result, but it's neat because it shows that that, as also happens for the equations on Higgs bundles, sometimes if you have an unstable bundle, you can stabilize it by choosing an appropriate Higgs term. Okay, so these were our first results on the system, and but maybe some more interesting things can be said in a special situation where the system is written in symplectic coordinates. So this is now some more recent results that we have on the problem. And okay, so we assume that we have some large set over which we have a system of complex coordinates, and we consider tensors that are invariant under translations on the imaginary part of the coordinates. So effectively, all the tensors we consider now will depend just on the real part of the coordinate. Okay, in particular, if we consider a Kähler form that depends just on x, then we find that in the system of coordinates, we can describe omega as, well, as having a local potential. And the matrix of the metric will be the Hessian of this convex potential. So it is an observation by Abreu that if we now consider the Legendre dual, so let's call U the Legendre dual of this potential for the Kähler form, then the scalar curvature has a particularly simple expression. So here you see we are taking the Hessian of U. So the Hessian of this function that is called a symplectic potential. Then since V is convex, also U is, and this is a positive definite matrix. So you can take its inverse, and the scalar curvature is then obtained by taking a trace of the second derivatives of this. So you see it is a fourth order differential operator, highly nonlinear, but still it's quite easy to write down in these coordinates. Okay, so our question is, what does the Hitchin-cscK system look like in this special set of coordinates? And okay, so first we restrict to considering deformations of the complex structures that depend just on the first, on the real variables. And then our deformation alpha is described in terms of some symmetric complex matrix Xi. And the Hitchin-cscK system has this shape. So the first moment map equation, recall this was this had this expression in general, becomes a much simpler condition on second derivatives of Xi. So this is reminiscent of Abreu's equation. And the more complicated real moment map acquires a, let's say, slightly more pleasing shape. So here, this term here, so we have a composition of Xi with the Hessian of U. So we take the Hessian of the symplectic potential, and this is just matrix multiplication. This whole term is a rewriting of the endomorphism alpha conjugate. And so you take this square root, multiply it by the inverse of the Hessian, and then take this trace on the second derivatives as in Abreu's equation and also as in the first moment map equation. So you see when alpha is 0, then you get Abreu's equation. And in general, well, it's much easier to study this system rather than the more general one that I've written in the previous slides. But then, of course, this system describes the Hitchin-cscK equations only on this open dense subset over which we have these special coordinates. So, well, to make sure that they compactify to actually give us a solution of the Hitchin-cscK system, we have to impose some boundary conditions. And the boundary conditions will be different depending on the topology of the problem. So the first case that we can study with this approach is that of abelian varieties. So in this case, the boundary conditions is just periodicity. So we impose periodicity of this Hessian matrix and on the deformation of the complex structure. And this is the system of equations then that describes actually the Hitchin-cscK problem on an abelian variety. And maybe the more interesting case instead is that of toric varieties. So toric varieties are very important for the theory of the CSCK equation because they, I mean, on a toric variety, we have this very famous result by Donaldson that at the CSCK equation, I mean, having solutions of the CSCK equation is equivalent to K-stability. Well, of torus equivalent K-stability of the variety itself. So this is an important test case for the CSCK problem, and it turns out that maybe it's also an important test case for our more general system. So in this situation, the boundary conditions are very well known by the work of Donaldson and others, and they're called Guillemets boundary conditions. While for Xi, it's not clear what they should be, but we will find out shortly. So first, just to spend a couple of words on for abelian varieties, essentially nothing interesting happens. So the problem is unobstructed, and anytime you have a solution of the first moment map equation, you can find a symplectic potential that solves also the real moment map equation. Now, maybe a more interesting aspect of the problem is that there is a variation, a characterization of the real moment map equation that gives us also some uniqueness result. Now, well, I don't really want to go into the details because they they are a bit complicated. I just want to show you the shape of the functional that gives the second moment map equation. And so it is written as the sum of two terms. So the first piece here is the periodic K energy. So the functional that we are used to see in the CSK context. And we have to add something that depends here, these delta i's, these are the eigenvalues of alpha conjugate. So this is a huge symmetric function of the eigenvalues of alpha conjugate. And we just have to add some piece here to make it a convex functional that has that equation as a first variation. Okay, but essentially the situation on an abelian variety is quite easy to describe. Now let me go maybe a bit more quickly on the toric case. So on a toric variety, we have these coordinates that are defined on some open, on some polytope inside Rn. So we'll have a closed polytope P inside, well, in this example, R2. And the boundary conditions for the symplectic potential just tells us that as we move towards the edges of this polytope, then the Hessian, so the metric, acquires some singularities. So it has some prescribed singularities in the normal direction to the side. So this is the normal direction to the side of P. And these are very well known, but okay. The more interesting thing is that also the deformation of the complex structure can essentially, I mean, its boundary conditions can be enclosed in the boundary conditions for the symplectic potential. So we have some smooth matrix that describes Xi up to the multiplication by the Hessian matrix of U. And this has a first interesting consequence that, for example, we find that to have a solution of the first moment map equation, the deformation of the complex structure cannot be an integrable deformation of the complex structure. And this is sort of interesting, but also maybe more interesting still, we find that the Futeki invariant, so the Futeki invariant is an obstruction to having solution of the usual CSK equation. But it turns out that it's also an obstruction to having solutions of the Hitchin-cscK system. So the real moment map equation can be solved just when the Futeki invariant of the surface vanishes. Now, this is more or less enclosed in this big lemma that I've written. So this is just some integration by parts. Okay, so here you see the same expression that was present in the moment map equation, and then this is just integration by parts on these two variables I and j. And okay, so to make the long story short, it turns out that so if f is an affine linear function, and if this whole term is a constant, so that we have a solution of the HCSK system, then we find this condition. So here, this condition here has to hold for every affine linear function f. And you see then that it's not a condition anymore on the symplectic potential, but just on the combinatorics of the polytope. So we find a condition on the manifold that poses an obstruction to having solutions of the HCSK system. And yeah, and as I was mentioning before, this is just the Futeki invariant of the toric surface. And so this is precisely the same condition that you find if you analyze the CSK system, sorry, the CSK equation rather than the Hitchin CSCK system. So, well, we did not expect this, but it turns out that the Futaki invariant is an obstruction to much more than the CSCK equation by itself. Okay, so this is more or less everything I wanted to tell you about, and everything we have as far as results for the study of the system. So I'll leave you with some questions here that probably won't be answered anytime soon, but maybe if some of you wants to think about them, that would be nice. So thank you for listening to the seminar, and if you have any question, just feel free to write.
Okay, thank you very much. Okay, maybe my first question is about your questions, actually, because I think you didn't have the time to give some comments about them. I mean, there are 3 questions you added. Mm-hmm. So can you do, first of all, some comments about this last slide?
Well, no.
What do you mean by hyperkähler and so on?
So, to be honest, these are really wide open right now. So I haven't really given much thought about them, mostly because there are some huge technical difficulties into investigating this the modular space of solutions of the equations. And so the biggest problem,
this is what you mean in the first question? What do you mean by hyperkähler quotient structure? That there's a...
This is what I meant, sorry. So we are able to do so in at least in the one-dimensional case. So over a complex curve, but well, this had already been done by Donaldson. So he managed to define using these hyperkähler equations. He defined a hyperkähler metric on a thickening of a Tachymuller space. So you take Tachymuller space with its Weil-Petersson metric, and you can sort of enlarge it in a cotangent band inside its cotangent bundle, and define a hyperkähler metric there using this parameterization of the solutions that I mentioned in the one-dimensional case. But in higher dimension, it's really more complicated to study this set of solutions, because well, there are some issues with the let's say the complexification of the action. So, maybe those of you who are more experienced with the CSCK setting know that there are some problems to tie the CSCK equation with some stability notion, also because the group of Hamiltonian symplectomorphism, so this group, the group G of Hamiltonian symplectomorphism of X and omega 0, this doesn't have a complexification. So there is no way to sensibly define this thing. And this poses some unanswered questions yet, particularly for the second point here. So you sort of have try to circumvent this problem of non-existence, but it is quite harder to do it for the HCSCK system than it is for the CSCK equation. And the third point is just inspirational, but I haven't followed this part yet. The first problem for which it will be natural to do so is maybe for the Kähler-Einstein equation, and well, then that is also an infinite dimensional moment map, but it's a bit more difficult to work to define this hyperkähler structure in that case.
I mean, of course, this is one case of the CSCK problem. So one can ask if actually in the final case, your system of Hitchin-cscK system is easier to write, or only making appear Monge-Ampère type equations.
So then this is a good question. And so remember, we have this scalar curvature term, this S minus S hat, plus the divergence of some vector field, right? So in the Fano case, or in the canonical polarized case in general, this might become easier if you manage to write the divergence of this vector field as the Laplacian of something. Okay, so if you manage to solve explicitly this equation for phi, so you need an explicit phi solving this equation, then the Fano case, or in general the canonically polarized case, would become quite simpler. But I mean, this seems like a silly problem, but it's actually, it has proven to be a little bit more difficult than I thought. So I haven't been able to do so yet.
Okay. I imagine now, I have plenty of questions, but I imagine lots of people want to ask questions, so I'll let the audience ask questions.
Yeah, I have a question, if I may ask. Can you show us the previous slide, please, with the lemma?
Okay.
All right, here we go.
Let me erase maybe this.
Yeah. So yeah. Actually, you can keep it. Anyway. So this first term that you just clean up. I think it's what is inside is a positive definite matrix.
Yes, it is a positive definite matrix.
Okay, but then your argument actually shows more. It shows that if you have a solution, the polytope is uniform stable. And therefore, yeah. So my question is that true? And effectively, you will have a constant scalar curvature metric if you have a solution.
Yes. So I'm working on this in these days actually. So I can tell you that. So the lemma, as I've stated it, is just for smooth functions on the whole polytope.
But there is a general argument actually for scalar structures.
Yes.
That if you have something positive definite, you can get something positive from piecewise linear function. And so
yes, exactly. So yes, this is exactly what happens. So actually, in this case, you are correct. So my, let's say, last findings show that actually this should be greater or equal than 0 for every f.
You can do better actually. You can do it uniformly. It's an argument of.
Oh yes. Sorry, just to.
And then you can go back in existence of constant scalar curvature.
Yeah. So in fact, an obstruction for this. I mean, sorry. So this Hitchin-cscK system on a toric manifold can be solved only if you can already solve the CSCK equation. So this seems to be the case. That is correct. Yes.
So my next question is, do you have a general deformation argument starting from constant scalar curvature? Can you always find solutions to your system for some sort of a small deformation data, or?
So the answer is yes, at least if you're in the case of when you have no holomorphic vector fields on the manifold itself. So if the linearization of the scalar curvature is an isomorphism, then yes, you have some perturbation argument of that sort. Yes. So
I guess the Toric framework gives you another example where you can expect such deformation.
Yes, exactly. So the Toric framework is a bit. I mean, it's a bit more interesting. Because I think I might be able to not just to give a perturbation result, but maybe it would still be a perturbation result, but maybe a slightly more explicit one. So give some explicit bounds on some Holder norms for the deformation of the complex structure. But yes, you're correct. Indeed, in this case, we have uniform K stability. Yes.
But a priori, you could have a solution to the CSCK metric on a toric without having a solution to the Hitchin system.
Well, you just have to take a deformation of the complex structure that is identically 0. So okay. you just take alpha equals 0, and then it becomes the CSCK problem. So yeah, the sort of more interesting question is that of maybe obstructed, of K unstable varieties, where you might hope to find some Hitchin term that makes it become stable. But
you could, no, my question was, you could have a CSCK, but you could find some deformation. Could you find some examples of that, a CSCK, and some deformation which are not Hitchin-CSCK?
Some deformation that are not. Sorry, maybe I misunderstood. You mean if I can find?
Could you find an example of a CSCK toric? But for certain alpha for your variable, your system, for certain choices of your system, you still don't have a solution. Of course, you have a deformation theorem, right?
Yes. Okay, so the answer is not yet. I don't really have many examples of let's say explicit solutions or non-solutions.
Or non-solutions, I see. And in the case of the ruled, that was interesting case, the ruled surface where you did the computations. What is interpretation of the equivalent of the Higgs field?
So the field. Okay, let me go back a few slides. Well, maybe more than a few. Sorry.
Is that a geometric interpretation?
Okay, so
yeah,
have here so the trivial bundle plus the canonical, and the Higgs field here is a deformation of the complex structure of this bundle. So you take the standard complex structure here, and then you take a Higgs field that sort of let's say mixes the complex structures of the trivial bundle and the canonical. So you modify this bundle a little bit, so that maybe it's not split anymore or something like that.
But in that case, we have an extremal metric also, right? So on this ruled surface. So is there a relationship between the extremal metric and the Hitchin-CSCK system that you have?
No, I mean from the equations, it's not apparent that there is a direct relation, and I do not have examples of manifolds who don't even admit an extremal metric that have a solution of the H-CSCK system. So I mean, for now, I really have a very small basket of examples. And
okay, you didn't consider the case of P of E, where E is a rank 2 vector bundle, which is unstable.
Well,
over a curve.
Well, this is unstable, but you mean a non-decomposable maybe?
Indecomposable, just meant for the unstable.
Yeah, for now we haven't considered that yet, but I mean it's one of the many things that I should be working on in the next few months.
Okay.
But, yeah, I mean there is a natural number of things to check, and unfortunately I have checked just a very small number of them yet.
Like this. Okay. Are there any other comments or questions? Nobody raised its hand. So I suggest that we thank the speaker for his very nice talk, and hope to see all of you next week. Thank you so much.
Thank you.